Thanks a lot for the introduction and thanks for the invitation. So I didn't want to talk about the stuff that I'm always talking about, so I briefly talk about hash function security, and then I will come back to hash-based signatures. As a brief reminder, who of you took Crypto 101? So essentially everyone is, okay, so I probably don't have to be too detailed about this. But so for a cryptographic hash function, I'm considering generally compressing at most length-preserving function that takes an additional input, which is the key, which you can think of as a function description that's publicly known. And well, sometimes I might even omit the key, and otherwise I write hk of x. And from these functions, we want three properties, or actually more, but the main three properties that we want are collision resistance, which says it is hard to find, given the description of the function, two inputs that collide, so that lead to the same output value, where of course giving 2 times the same value is forbidden, because that would be uninteresting and easy. The second property is second-preimage resistance, which says given a function description and an input, it's hard to find a colliding value for this input. And preimage resistance, or one-winner, says it is hard given a random image, well actually an image of the function generated by first sampling a random domain element and hashing this one. It is hard to find a matching input such that this input is hashed to this computed image. Right? So I give you an image under this function and ask you to give me a domain element which hashes to this image. Okay, so these should then probably not be new to you. If I talk about quantum security worlds, then I briefly want to establish some terms, because this got somewhat wide at some point. And Tommaso Gagliardoni, a colleague of mine, did in his PhD thesis kind of a nice distinction of different security settings. And so the first setting he describes as QS0 is just the classical security games which we have, which most of you know from crypto papers. So we've got the classical Alice that wants to talk to a classical Bob, uses a classical channel for this, and our adversary is also classical. If you move to QS1, which is what we usually call post-quantum security, then Alice and Bob actually remain exactly the same. But now our adversary is assumed to maybe have quantum computing abilities. So the adversary might have a quantum computer that it can use. And so that means the adversary can run local quantum computations. This still means that if the adversary communicates with honest parties, all this communication is classical, because the honest parties are classical, right? However, if we start to use things like idealized models, like the random oracle model, for example, then these model things that the adversary would usually implement locally on its computer. So in this case, on its quantum computer, which means we have to give the adversary the ability to actually query these functions in superposition, so using quantum states. And so that means all kind of functions that the adversary would normally implement locally, and all kinds of oracles that do not contain secret information, you would give the adversary quantum access. And for all kind of remote functions or oracles which are secretly keyed, so think about the decryption oracle in some CCA game, you just get classical access. And then the third world is QS2, which most people then call quantum security. So here also Alice and Bob are quantum, or have quantum computing abilities, and are communicating over some quantum channel. And so in this case, suddenly also these kind of remote function calls and secretly keyed oracles have to allow quantum access. And this is the setting where I think some of you might have heard talks about breaking symmetric key crypto using Simon's algorithm. So Alex May and Gregor Leander actually had a paper on this some time ago. So this is the point where really quantum algorithms can run at full potential because you really don't have to have this point where you actually have to make classical queries in between. And there you can actually, we know that we can break symmetric crypto, for example, or certain secret key constructions. Sorry? Well, asymmetric crypto we can already break in the post-quantum setting a lot. For symmetric key crypto, in general, there's this assumption, well, the best we can do is Grover. Grover actually gives you a square root speed up, so we double the security parameter, we are fine. If you are in this QS2 setting, then, for example, Evan-Mansour is entirely broken. So Evan-Mansour you can break with the polynomial number of queries. Right? So that shows you maybe the power. So that doesn't work in the post-quantum setting. There was a paper now at AsiaCrypt which showed how to use some of these abilities from the Q2 algorithm actually in the post-quantum setting, but that goes too far for today. So in general, in this talk, I will only care about this QS1 setting because that's the one that we actually are interested for the foreseeable future. So everything else until users get quantum computers, let's see if this ever happens. I mean, because of the power plant which you would have to build in your garden, it's somewhat unlikely. So what does this mean for hash function security? The first thing is we have to reassess the generic hardness of functions. So there is this thing that Grover is optimal and seems to be the best you can do. But Grover, or the analysis of Grover's algorithm is actually a worst case analysis. But if you redo this analysis, that's something we did in 2016 and Sandry for collision resistance in 2015, then it turns out that really the best you get in terms of speed up is this quadratic speed up. So classically, if you want to break preimage resistance and you do Q queries, then what you get as success probability is Q plus 1 over 2 to the n. Because what you can do is you make a guess, you evaluate the hash function at this guess. If you hit the image that you were given, then you're done. Otherwise, you make a new guess. You can do this Q times. Well, then actually you can make an additional guess if you were not successful until this point. So with Q queries, you essentially test Q plus 1 values, and it gives you this Q plus 1 over 2 to the n success probability for an n-bit hash function. And in the quantum setting, you get Q squared over 2 to the n. Oh, actually, this is the post-quantum setting in this case. If you have any questions, then just ask in between. Now, these bounds actually are just for generic attacks that do not care about any kind of structure that the hash function potentially admits. And so at this point in 2016, we started to look into about actual hash functions. So what does this mean if we really look at structured hash functions? If you look at how hash functions are built, then we usually start from some fixed input size and also fixed output size building block like a permutation or a block cipher. From there, we've got an optional step in between where we build a compression function. And then from this compression function, we move on to build a full-fledged hash function. This first part is where we got the bit pushers that essentially use engineering techniques to decide how to build a good permutation or a good block cipher and then analyze these using cryptanalysis. And from there on, we use generic transforms and back up the security with a reductionist proof. So we bootstrap from this engineering cryptanalysis approach. Now, these things are not random anymore because they are structured the way we built them. So when you look at the Merkle-Damgard construction, which was the main mode until a few years back for hash function design, so this was used in MD5, SHA-1, SHA-2, RIPE-MD, and so on, then, and that mode I guess most of you have seen before, then actually all the proofs for the single properties also translate to proofs for the quantum properties so far. So we've got proofs for collision resistance, one-wayness, even something called collapsingness, which is kind of a quantum version of collision resistance, which I will not go into detail today. And all these proofs actually you can also do for in the post-quantum setting. If you move on to sponges, to the SHA-3 construction, then things get a bit nasty. So sponges look as follows. We've got an internal state which is split into a capacity and a rate. And during the absorbing phase, where we process the message, in every step we XOR the next message block into the rate part of the internal state. Then we apply some internal function, and then we take the next message block again, XOR it into the rate part, and so on. And when we have absorbed the whole message, then we can produce arbitrarily many output bits by just grabbing the rate part of the internal state. And after we output this, we apply the internal function or block function once more and can get another block from the rate. Okay. Now the SHA-3 people actually, or the sponge team, had a really nice idea or approach. Instead of giving a security proof for every single security property, they said like, yeah, okay, forget about this. We give one proof, namely we show that a sponge starting from a random permutation actually behaves like a random oracle as long as an adversary doesn't make more than 2 to the c, where c is the capacity, over 2 queries. So for practical parameters, if you have, for example, shake 128, then this means, which is a version of SHA-3 where you can produce arbitrarily many output bits. This means that as long as you do not make more than 2 to the 128 queries, this sponge actually is indistinguishable from a random oracle, even if you get access to this internal permutation. Now this proof is inherently query-based. So the problem is that the proof really requires knowledge of the queries to this to the internal function. And also it's a bit, what you do is you say, if a query leads to an internal collision, which means a collision in this capacity part, then that's a bad event, and that's the point where the proof goes wrong. And then you argue why it takes at least 2 to the c over 2 steps until such an internal collision could happen over the randomness of the random permutation. The problem is in the quantum setting, this happens with the first 2 queries, because you can just query the superposition of all messages, and then you query the superposition of all messages again, and then you've got a collision somewhere in there. This is, of course, of no help to you, because the collision will have such a low amplitude that you can actually not extract a collision from there. But this means the proof just goes wrong. Like there's no way to get this proof working exactly the way it is. And so we set out to look into this, and in the first step, we then started to really prove the single properties we had in the beginning, so collision resistance, second-preimage resistance, and preimage resistance, and also this collapsingness notion. If this internal block function is a random function or a random one-way permutation. The proof did not go through if you use an internal, if you use just a random permutation, which is invertible, because then the arguments we use don't work anymore, and you have to look at the whole construction at once. For those, we also came up with matching quantum attacks which meet our bounds, so that means the proofs are actually tight. And last year we came up with the proof which shows that sponges are quantum indistinguishable, which means if an adversary gets quantum access to the sponge construction, but not to the internal function, it can actually not distinguish a sponge from a random function. So that essentially gives you quantum secure PRFs or max if you key the block function. And if they are quantum secure, they are also post-quantum secure. All right, so quantum secure is just stronger. What we're still missing is a proof of indifferentiability for random sponges. So that's something some of my co-authors, so especially Jan Tchaikovsky and indirectly Christian Schaffner, then are working on. They've got a paper online about this, but that still has some technical issues. So They might have fixed this by now. They think they have a solution, but so this is still one of the topics that actually would be interesting to see if we can manage to really re-establish this indifferentiability from a random oracle also for sponges. Okay, so that's the one part that changed and that we started to look at, and there's still a lot of little issues that you want to look into. Yeah.
So if you could redo the SHA competition or the hash competition now in the Q-ROM setting or with the quantum setting in mind, would you recommend sponges or is there want to go for another down guard or invent something completely new? Is there some alternative?
I think the problem is rather that we cannot say too much about it yet. So there are now, so also indifferentiability for Merkle-Damgard was just proven, well, essentially by a paper which appeared at Last Crypto, using a new technique to think about quantum random oracles. And so currently this technique is only written down for random functions. It doesn't work yet for random permutations. The problem is, so what they do is they build a superposition of all functions in space, and that's something you can pretty easily do, because if you write it down as a function table, as every position in a random function is independent of the others, you can just do a Hadamard transform on this one and get the superposition, and that doesn't work for permutations anymore. But if this is overcome, I guess we will actually be able to establish also bounds for sponges. And then they have a lot of advantages that Merkle-Damgard doesn't have, especially like this soft structure that you can generate arbitrary length outputs. And it's already built in, and you can do duplex and things like this. That's something we don't have in a Merkle-Damgard construction. And I mean, SHA-2 is still there, right? So it's actually, for the next topic, most people use SHA-2 because we now got hardware acceleration for that. So I think, but so far I think we're not at the point where we can say it would have been better to pick one or the other yet. So there's still a lot of things to be answered. Any more questions about that part? Yeah.
Maybe I would like to ask about the different, maybe it's too specific, but about the difference in Merkle-Damgard and sponge construction regarding side-channel attacks. Can you, so for example, in Merkle-Damgard, there are these lucky protein attacks where depending on the length of the input, the number of blocks are hashed, and depending on the number of blocks that are hashed, then you can find out, extract some secrets and so on. So
I think this would work exactly the same.
Exactly the same, so there is no difference.
No, the advantage is a bit that that the block size is bigger for sponges.
Mm-hmm.
But I think otherwise,
Also, like,
especially for something like Lucky 13, I don't see how this would actually differ, because you've got exactly the same issue that if you have one more block, it takes longer. You've got one permutation round more. Yeah. So one thing a bit nasty with the sponges is that for everything, so for example, there was a paper on leakage resilience of sponges, and they also have exactly the same issue that we had, that if you want to reason about steps of the function, you actually need a one-way primitive. You need either a random function or a one-way permutation. But if you have a permutation where you can go backwards, then the whole argument breaks down. Because then essentially your reasoning has to start from the initial state, which is all 0. And then you have to essentially reason about the whole thing at once. You cannot really break this down into single steps, and this makes it really hard to work. Okay? So there are still several things. For example, I didn't look into compression function design. I didn't look into permutation design. There are a lot of open questions still in this area, but that's also largely, or in large, one part, this is work for the symmetric key people to check if you can actually do quantum attacks better on on these permutations. So that's something that Marianne Plasencia in Paris is working on, among others. And there is some work that we currently do on compression function design. But a second thing that I want to talk about now is new applications. It's actually not new. So actually, Real World Crypto, Merkle got the Levchin Prize. So and Merkle invented hash-based signatures end of the 70s. Well, Lampert came up with a one-time signature scheme mid-70s. So these actually come from the time where public key cryptography was invented. However, these were considered pretty uninteresting for a long time, and just recently interest sparked. So we had this discussion on the way to lunch. I was working on this during my PhD, and I didn't get my papers into any big conferences because people just found this uninteresting. Now we're at the point where we've got 2 RFCs for so-called stateful hash-based signature schemes. And NIST is currently working on has a draft for a NIST technical guideline, special publication, which is essentially a NIST standard on these things. So brief recap how these things work. Some of you might have heard about Lampert's scheme. So Lampert's scheme is a so-called one-time signature scheme, and that's where hash-based signatures start from. So these schemes look as follows. You've got a secret key which consists just of random bit strings. And if you want to consider 1-bit messages, you need 2 random n-bit strings as your secret key. And your public key consists of the hashes of these 2. Right? And now if you want to sign a message, you actually assign a 0 and a 1 to these 2 bit strings. If you want to sign a message 0, you publish the secret key element which you assigned to 0. And if you want to sign a message 1, you publish the secret key element which you assigned to 1. And you also have, I didn't say this, but the public keys get the same labels. And what a verifier would do is it hashes the signature and checks that the hash actually matches the corresponding public key value. Okay, so if I got the message bit 0, then I hash my signature and check if it matches my Y0 value in the public key. So how do I go from there, from 1-bit messages to n-bit messages? Well, we use n pairs of these things. And thereby we can sign n-bit messages. You might say this is really inefficient. Yes, this is really inefficient. We can do somewhat better. So there's the Winternet scheme, which gives you a logarithmic factor compression. But that's currently somewhat the best we can do. There are some proofs which say you can go slightly below the compression factor of Winternets, but then the schemes get super complicated. And so these optimality proofs only apply to a certain class, but currently it seems as if this is really somewhere close to optimal. So now a one-time signature scheme doesn't buy you much, because this means I have to communicate a one-time public key to later on certify a message. How do I go to a many-time signature scheme from there? That's where Merkel's idea comes in. So he said if you want to do some power of 2 signatures, let's say 2 to the h, then you take 2 to the h one-time key pairs, and then you build a binary hash tree on top of the one-time public keys. So my leaf nodes in the tree are now the hashes of the public keys. So to be clear, this means I really take all the public key values for one key pair. So n of these pairs, if I want to send n-bit messages, hash all of them together, and this hash becomes one leaf. And then I built up a tree where every node internally is the hash of the concatenation of its 2 child nodes. Okay? So I guess most of you have seen a Merkle tree, the one place or the other before. So this actually kind of authenticates all these one-time public keys. My new public key of this tree scheme is the root node of the tree. And if I want to sign a message, and the secret key consists of all the one-time secret keys. Now the good thing is that these secret keys are all random bit strings, so I can just generate them pseudo-randomly using a PRF, for example, or a PRG, and just store a seed value and then generate them as I need them. So I can have a secret key size of essentially the same size as the public key, namely a single hash value. And now if I want to sign a message, the first thing is I have to make sure that I do not reuse a one-time key pair. Right? So one way to do this is I use these key pairs from left to right and just mark myself where I currently am and keep this as a secret state, as a public state in my secret key. And then if I sign, for example, the second message, I take the second one-time key pair, I put into my signature the index of this key pair, then I put the one-time public key and the one-time signature on the message. And in addition, I have to put this so-called authentication path, which is all the internal nodes of the tree, which are siblings to the nodes that I can compute from the one-time public key that I used. And this is necessary because later on, if a verifier wants to verify the signature, the verifier can first check the one-time signature using the one-time public key. And then later on, it can verify the one-time public key computing an alternative root value. So you start from here, you hash up, then you've got this node, you can hash these two together. You've got this node, so you can combine these two again, and eventually you will end up at the root. Then you compare the root that you computed to the public key value that you were given, and if these two match, then your signature was valid. Clear? Okay. Now, if you want a key pair with which you can do a lot of signatures, then you have to note that during key generation, you have to compute the root. So if you want, for example, a key pair that can do something like 2 to the 60 signatures, then if you do this with a single tree, you have to do 2 to the 60 one-time key pair generations. That's like, if you don't have the whole Bitcoin mining network at your disposal, this will take forever. So one way to do this, or to deal with this, is you build what we call a hypertree, which is essentially a certification tree. So for the more IT security people in the room, think of it as your own little PKI. You start with a key pair that can do, say, 32 signatures on the top layer. And then on the next layer, you put 32 trees, each of them, again, that can do 32 signatures, and sign all the root nodes with your top level tree. And you reiterate until you arrive at the number of one-time key pairs that you wanted on the bottom layer, and those you actually use to sign your messages. And for the stateful schemes, you can do a lot of optimizations there, but as we want to go to stateless schemes later on, the main point here is that key generation cost goes down from 2 to the h to 2 to the h over d operations if I use d layers to actually build my tree. Okay, so these are how the stateful schemes work, and a lot of work that happened in the last decade was on minimizing the security assumptions. So Merkel's original scheme, if we take a slight optimization of it, then this essentially needs a pseudo-random function, then a collision-resistant hash function that is also preimage resistant, and the proof would be non-tight. In 2008, I think, Eric Dahmen, who was my predecessor in Darmstadt working on this topic, with some colleagues came up with a scheme which would only require a pseudo-random function family, and then not a collision-resistant, but a second-preimage resistant hash function, and which is also preimage resistant. This is interesting because if you want a collision-resistant hash function, then you need 2 times the security level as output length of your hash function. All right? If you need a hash function which just is pre-image or second pre-image resistant, you need the same output length as the security level that you target. As all our values in the signature are just hash values, by reducing the security requirement from here to there, from collision resistance to second preimage resistance, I actually get a factor 2 improvement in the signature size. But the scheme was pretty inefficient, so they really used the Lampert scheme that I introduced in the beginning, and the proof was non-tied. For XMSS, we changed this a bit and came up with a scheme which was more efficient than MSS-SPR, but otherwise had the same properties. And then for the scheme that we've got described in the RFC, we moved to something where we don't need the pre-image resistance anymore. At least not as a property. We derive it from second-preimage resistance and some additional structural assumption, which turned out to be too annoying to build in a hash function, so that we actually had to look into something better. So there we get a tight bound, but we earn kind of a bad assumption, and this was something that we recently worked on, and which led to a new security property or requirement for hash functions, which we call decisional second-preimage resistance. And to briefly explain what happened there is the following. If you think about Lampert's scheme, for those of you that know security reductions a bit, I think it's somewhat obvious if you see an adversary that saw, for example, a signature on a message 0 and then comes up with the signature for the message 1, must have broken the pre-image resistance of the scheme, right? So you get a pre-image finder, the pre-image resistance of the hash function, because you find something which hashes to y1 without seeing a pre-image of y1. Now to actually use this adversary as a pre-image finder, what happens is you have to place an image that you want to invert into one of these two values. If you guess, for example, the adversary will invert y0, then you put it here. Now you've got one problem. The adversary is allowed to make one signing query. So if the adversary asks for the signature on the 0 bit, you would have to answer with this value, which is a pre-image of y0, but that's exactly what you wanted to compute, right? So you would fail in this case. And this means you essentially get a guessing probability of 1/2 that you actually put your challenge into the right place. If we could use a pre-image finder to actually find second pre-images, then this would be a lot nicer, because let me briefly tell you the reasoning and then you can tell me where I'm wrong. But the reasoning is if I start from some x0 that I've got, I hash this, and this becomes my public key. And now I do this actually for both. This means I can answer all the signing queries. If the adversary forges, it will give me a pre-image of one of these two values. But the adversary doesn't know from which value I actually computed this hash, right? So as this function is no permutation, there's a high chance that there are actually at least two pre-images, and that the adversary will give me exactly the one that I didn't know, which would mean I found a second pre-image. Should we turn down the heating, or am I too? So if we could actually get this reasoning working, then we wouldn't have to abort in any case, and we would always have our reduction work. The problem is that there are cases for functions where this doesn't work, and so this is essentially what I said before. The cases where it works is when what we call decisional second-preimage resistance is hard. So decisional second-preimage resistance essentially says it is hard to reliably determine if an input has a colliding value or if it doesn't. And you can actually show that if you have an adversary that breaks pre-image resistance, then that adversary either breaks second-preimage resistance or decisional second-preimage resistance.
What does it mean? It's hard to determine. What's given or what? I'm adversary.
So the adversary gets an x and is asked to determine if this input x actually has a collision in the domain.
Exists x primes
such that they collide. Actually, if there exists at least one. And it turns out the important thing is it has to be hard to pick or to detect the elements which do not have a second one. Because this is exactly where this reduction actually goes wrong. If you have an adversary, so you can think about an unbounded adversary, which only, like always, looks for all the pre-images, and then only inverts if the target doesn't have a second pre-image. Because in these cases, it will always give you the element that you already knew. And so to exclude this, this case, you actually need this property. So for compressing functions, this is almost trivial. OK, so actually, to reliably determine this better than guessing, I should have added. So here we're actually talking about an advantage. So if you have a random n-to-n bit function, the best you can do is just always output 1 and always say, like, yeah, this has a second pre-image. And then with probability 1 minus 1 over e, you're correct. And just with probability 1 over e, you're wrong. But if you exactly subtract this trivial advantage, then you come to the point where it gets interesting. So if you can do better than this trivial step, that's what has to be hard.
Where is that an issue in which function? And usually all functions that we care are have some sort of regularity, you know? Where this
That's exactly the bad property or the bad assumption that I made for these cases. But if you have an n-to-n bit function, you don't have this regularity anymore. So exactly.
End-to-end random function, that's the sweet spot.
Yeah.
Where things get. Okay.
So that's exactly where things go wrong. And this is, yeah. So I actually, those slides I took out, maybe I should have left those in. That's exactly the point where things go bad, and then you need some additional assumption to make this work. Well, and actually, now you could say, well, you're introducing a new assumption, but we were able to show that this is also hard for quantum adversaries. So we can give a quantum query complexity lower bound for adversaries in breaking this property, which is actually the same as for second-preimage resistance. So no quantum adversary can do better than achieving a success probability of q squared over 2 to the n, as long as the function doesn't have any internal structure which actually deviates from a random function.
So you mean for a random n-to-n bit function?
Well, actually for any n-to-n or compressing function. But the n-to-n bit case is the worst case. So, so as soon as you have a 2 n-to-n bit function, the thing is trivial anyway. There's just no advantage that you could reach because there's always a second preimage. Yeah? I mean, I can also give you more details about this later if you want. So I shrink this a bit because it sounded to me as if people here would be interested in also hear about stateless hash-based signatures, because those are the schemes which are currently in the NIST competition. So this started, like the efficient scheme we proposed at Eurocrypt 2015. So stateless hash-based signatures go back essentially to two proposals by Goldreich from the early 2000s. And so the idea that we built on is the following. If I have a security parameter, say 128, and want to build a stateless hash-based signature scheme, I can do it as follows. So I built a huge Merkle tree, a huge binary tree. And to get statelessness, I just pick a random index and use that one actually to sign a message. Right? Now this needs an immense tree to actually avoid index collisions. So you need something like a tree of height 256. And now to make this efficient, you cannot use just one tree of height 256, but you take this hybrid tree approach, And actually, at that point, they said, well, just use a binary certification tree of one-time key pairs. So you essentially take this hypertree approach with a tree of height 1, right? So every key pair is used to sign the public keys of 2 new key pairs. Well, and then you get an asymptotically efficient scheme. So that has polynomial runtime, so everything is fine, right? If you would build this, you get something like 15 megabyte signatures for already somewhat optimized and decent parameters, and and runtimes which are also in the several seconds, I think. Well, of course, you can generate all the one-time key pairs pseudo-randomly, so that's fine. But yeah, I mean, your signatures just get enormous. And so the Sphinx proposal was to actually follow this approach, but first use a real hypertree. So for example, there we use the trees of height 5. And then actually the key idea was at the bottom layer to not use one-time key pairs, but actually use something which is called few-time signature schemes. So few-time signature schemes are schemes that come from sensor networks, I think. And they can be used to actually sign a few messages. So in our case, this was something like 8 messages without using a state, and security slowly degrades. So with every signature, the scheme gets more insecure. And what you do in our case is you actually balance the probability that a certain number of collisions at a leaf occur with the probability that after such a collision occurring, you can actually compute a signature. Right? And that's the main idea. If you do this, you can allow a certain number of index collisions at the bottom layer, or a certain probability. And so you can actually shrink down the tree. And so for Sphinx 256, we then use the total tree height of 60, which is roughly like a factor 5 size improvement for the tree in the exponent. So that's quite a bit, I think. Now, when the NIST competition started, we started to look into how to improve the scheme, and we recently wrote a paper about this, which we call the Sphinx plus signature framework. The whole Sphinx plus team are actually a lot more people than the authors of the paper. So in the paper, we did more the theoretical analysis. The scheme design was done with all these people. And so what changed there was the first thing where we actually had to touch the scheme again was that NIST came up with this super annoying requirement that the number of signatures that have to be supported per key has to be 2 to the 64. That's because, I mean, you need a power of 2 in the exponent, right? I mean, how could you do something else? And they always use 2 to the 64. I mean, also, yeah, you might, no, there is no length field argument. I mean, for SHA-3, I can understand this because you might want to encode the length somewhere in the padding. But here, this was just arbitrary. And I think they were not aware that this is something that you actually have to pay with in signature size for something like Sphinx. Because the more queries you do, the higher gets your probability of index collisions, right? And while we don't care about a single collision, we care about multi-collisions. So if you have something like an 8 times collision on a leaf, that's where you slowly get into problems. Well, but for this, we had to touch the scheme again, had to increase parameters, and then we had a few ideas how to actually improve the scheme. So in the meantime, we figured out an issue which we inherited from XMSS on which Sphinx was based, namely that the non-tied proofs actually are caused by real attacks. So there were certain multi-target attacks that you could do to increase the security level a bit. So we had by then already figured out the solution, what I showed you before, to actually get tight security proofs, but that's something that we then included in Sphinx Plus. We changed the few-time signature scheme, which I will briefly go into in a moment. And we used something called verifiable index selection, which hardened the scheme a bit and thereby allowed us to decrease the security or the parameters a bit at the same security. And finally, we added optional non-deterministic signatures to allow for better side channel protection. So they had this problem: if you actually can force a smart card to always do the signing procedure, then you can actually start extracting key material. So if you add randomness in there, then you can protect against this. So briefly about the few-time signature scheme. So the one that we used in Sphinx looks as follows. You start with your message, and you map your message to an index set consisting of k indices. And then you've got something like a Lampert structure. So your secret key consists of a bunch of secret bit strings, and your public key consists of their hashes. And you just publish the elements from the secret key vector which correspond to your indices. Okay, so you've got a long vector of secret values, and you take your message to essentially pick up to k of them. And so a generic attack that you can run against this is you find a message such that all the secret key values which get selected by this index set you've already seen in previous signatures. Right? This is essentially, this is exactly the reason why security degrades over time, because with every new signature, the set of known secret key values gets actually larger. And so the probability that you can find a message which only needs secret key values that you've seen before gets actually higher. So you get more insecure. Now what happened in Horst, which was the scheme in Sphinx, was that we actually drew all these secret key values from kind of the same pool of secret key values. And so if you would have the same index, so these indices are just, you take your message hash, you split it into equal length chunks and interpret these as integers. So in theory, you could have a message which just requires one secret key value to sign, because you can have repetitions. And this actually significantly weakens the security of the scheme. What we did in Force is we use k-independent pools of secret key values, and every index picks from a different pool. This means that your total size of secret key values in the first moment gets larger, but you can actually shrink them again if you do the math to reach then the same security level. And in the end, your signatures get smaller. So this is actually where it comes from. So the cover-free sets were the first approach to get a provable secure version of this Horse scheme. And Horse essentially uses a computational version of cover-free set systems, because so that means it takes a hash function which it assumes to behave randomly and then thereby picks the elements. If you use the cover-free set systems, then your signatures get enormously large. But yeah, so this is roughly where the idea comes from. So the second thing we did in this step was we added an abstraction for these hash functions that we're using. So if you look at how hashing in these schemes progressed, that's something I didn't mention before, but so in Merkel's original proposal, you would take an input, you would hash it, you get your output. In XMSS, that was actually already in MSS SPR, for the tree at least, you take an input, you XOR it with a random value which is part of your public key, then you hash it. That's what we used in Sphinx. In XMSST, we added a key to the hash function, which you can think of as a domain separator. So this just makes sure if you see a bunch of images and you win when you are able to invert one of them, for every query, you actually have to select a key, which means the query does never work or leak information about all of the targets, but just about one. Right? And then, so that was what we use in what we now call Sphinx plus robust. So that's one construction. And then we've got the Sphinx plus simple, which builds on an approach that was used in LMS. And they essentially do the same thing. They name the parameters differently, but you can think about it as just take the key, take the bit masks, prepend it to your input, and then hash everything. The reason to do this is exactly the same as for this XMSST construction, but it's kind of the random oracle model version, where you say, like, yeah, as long as you stuff in enough domain separation, then everything will be fine. Roughly. In our case, for the XMSST part, we can actually reason why if you put things there, you actually get a security proof. And so this is something that for implementation people is somewhat annoying, and also for proof people, because every time you change this hash function construction, you're redoing the whole proof for the scheme. So we started, actually driven by the implementation people, to add this abstraction of what we call a tweakable hash function. So in addition to, so the function key now gets split into two parts. One part are the public parameters, which are really kind of the function description. And then we've got a tweak, which is different for every hash function call, and you can think about it as a nonce. Or in Sphinx, we actually use an addressing scheme, and every tweak essentially encodes the position of this hash function call in the virtual structure of the Sphinx tree signature scheme graph. Okay. And thereby you make every hash function call actually independent. So the public parameters make key pairs independent from each other, and the tweak makes every hash function call in your scheme independent of the other one. Well, and then your security properties get pretty nasty in the first moment. So what we need is, well, post-quantum, so skip about this, but then single function, which means we're taking a random but fixed public parameter set. Multi-target, so in this case, this means that the adversary can adaptively define targets consisting of a tweak in a message using an oracle which is already initialized with the public parameters. Then target collision resistance. So target collision resistance means that the adversary can actually specify a target for which it will find a collision, but without knowing the function family yet. And so in our case, well, the adversary does already get access to the function family, or to the function, but does not know the actual public parameter yet. And so after defining these targets using an oracle, it then receives the public parameters and has to find a collision. And the additional condition is, well, that the tweaks for the targets are actually distinct, so that these are really nonces, that they are just used once. Right? And actually, if you would reuse them, this would just harm insofar as that you would get a multi-target attack among the same tweaks. So this would not entirely break the scheme, but it would just lower the security level by a logarithmic factor of the number of reuses of a tweak. Well, and the second property we need is, again, a single function multi-target version of this decisional second-preimage resistance. And then, so we actually give 3 constructions for functions that achieve these properties. And so the first one starts with a standard model proof, but pretty massive public parameters, and just requires essentially second-preimage resistance and decisional second-preimage resistance for the underlying hash function. Well, these kind of multi-target versions, but no interactive assumption there. Then we've got an efficient construction which just adds public parameter compression using a QROM argument. And then the third one essentially uses this LMS kind of construction where you just prepend everything and there you get a QROM proof. And then from there we actually prove security of Sphinx Plus. And there, so the tweakable hash functions need these 2 properties that I just mentioned. In addition, we need 2 PRFs. One to pseudo-randomly generate hashing randomness. So the same as you do in ECDSA, you actually take your message, process it with the secret key that you got, well, one part of your secret key as key for a PRF, and then the outcome is used in randomized hashing with the message again. And then in addition, we need this post-quantum interleaved target subset resilience, and this is essentially this computational version of subset resilience. But yeah, I will not go into the details how it works in this case. So there are a few more things with this verifiable index selection which play in there and make it not just target subset resilience, but even something a bit stronger. Okay, so I'm almost done. Second to last slide, I think. So we compared Sphinx Plus to other proposals. So if you look at the original Sphinx scheme, then so these schemes all have somewhat different security assumptions and parameter sizes. So for example, for the original Sphinx scheme, you could only do 2 to the 50 signatures. And so as we didn't want to play with the other schemes, we then selected parameters for Sphinx Plus which matched kind of the conditions of the other schemes. So you can see compared to our starting proposal, we get almost a factor 2 decrease in signature size. It's still 29 kilobytes for the highest security level, but well, no, wait, sorry, 30 kilobytes. These are the cycles for sign. But you get a factor 2 speed up for key generation and for sign. For verify, it takes a bit longer because so we shifted or balanced some operations which appear comparatively more often in verification than in signing. And because we use this public parameter compression, we actually get our public key down by quite a lot. And we also shrink the secret key because the secret key actually contained the public key because you actually need it to sign. So that's the whole reason why this thing gets smaller. Then one scheme that was in the NIST competition round 1, but then actually was kicked out, was Gravity Sphinx. So Gravity Sphinx essentially took Sphinx and said, okay, we just go with collision resistance and live with it. The comparison here is somewhat tricky. So we can get significantly smaller signatures by something like 5 kilobyte. But then our runtimes are a bit worse for signing than for Gravity Sphinx, while the key generation times for Gravity Sphinx are horrible. And the reason is that they do some trade-off where they pre-compute a large top-level tree. So they make the top-level tree bigger than all the other trees and just store this entire tree in storage in their secret key. So that's also why their secret key is pretty massive. So this is the whole top-layer tree. But this gives them some speed up because they don't have to do these top 2 levels of computations. Yes, and so also there the comparison is somewhat tricky because they settle on collision resistance and yeah. The last thing is Picnic. So Picnic is still in the competition. Picnic takes a totally different approach. What they do is they give a zero-knowledge proof about knowing a pre-image of a hash function. And the zero-knowledge proof is using this MPC in your head paradigm. So this is something you can actually also do just using secret key primitives. Because the approach is entirely, well, and then you use a Fiat-Shamir transform to actually make this non-interactive. The approach is totally different from what we are doing. So the scheme has quite a bit different behavior. So while we take a lot longer for key generation, we're twice as fast for signing and almost a factor 100 better in verification. Our signatures are about 20 kilobytes smaller, and the other parameters for the keys are roughly the same. One advantage of Picnic that we have to admit is you can actually, because you've got this identification scheme structure, you can build all these kind of special signatures from this. Like if you want to do group signatures or something like this, you will not get this from Sphinx. That's something that might be possible from Picnic. On the other hand, Picnic really crucially relies on low MC, which is a low multiplicative complexity block cipher actually, which they use as one-way function in their construction. And if they would use something like AES, there was a paper recently which showed it's not totally dramatic for the signature size and runtime, but this would significantly harm them. So, yeah. And as you see, so here we actually used SHA-256. We didn't use Haraka, which is a dedicated short input hash function, which is similar to low MC in terms of analysis and aggressiveness of parameters. But we, so there we could probably even have shaped off a few more bits there. Okay, so to conclude, there are already several results which actually establish that hash functions are also secure in the post-quantum world. But for the strongest security notions of indifferentiability, we are still not there. And I think there are also some steps that we still have to take also for the compression function design if you do not just look at SHA-3. I showed one application in hash-based signatures where you see that we've got still new security properties coming up which we have to analyze in these settings. So this also needs tools. Some others I didn't discuss at all, so I also didn't look into the whole or discuss the whole QROM setting. So in some cases also just these old security properties do not suffice. So the collapsingness is actually motivated by cryptographic hash functions which are collision resistant in the post-quantum setting do not give you commitment schemes which are fulfilling the security properties that you might intuitively want. And so finally, although Grover's algorithm is optimal, there are still many open questions which we have to solve for hash functions in the post-quantum world. And I want to end with a nice citation of Vadim Lubashevsky, where he stated at Pico Crypto 2017, if you're signing something for the long-term future and 40 kilobyte signatures is not a problem, then use stateless hash-based signatures, for example, Sphinx. Well, at this point, Sphinx Plus was not out there, but I mean, if even the lattice competition is advertising our stuff, I think then we cannot have done too much wrong. That's it from my side. Thanks.